Hello everyone, assalamu alaikum. So in this lecture, I'm gonna teach you about photolithography process. Um, as I said last time, we're gonna learn about patterning in this subject, and we're gonna do patterning on photoresist, and also we're gonna learn on how do we do patterning on silicon dioxide as well. So before we move on, let's just recap on what you have learned before. So, so I want you to go through these two questions and try to understand what are the answers required for these questions. So, for example, the first one, when we talk about silicon dioxide as a mask for a diffusion process, how do you tell that the mask is more effective against boron or phosphorus dopant? And the second one is why do you need to use anhydrous hydrochloric acid 6% or less to be incorporated during your thermal oxidation process? What is the role of this incorporation, and what is it doing during the process? So let's continue to the topic for today. So we're going to learn about photolithography process, which is a printing process essentially. But the printing process, instead of being done by the typical, in comparison, if you look at your t-shirt printing, it's typically done by a screen printing process. But this one, in order for us to print our patterns or our circuit on the wafers, we need to do a printing process by using light. So this is called photolithography process. So photo there means light or photons. So this is the environment of a lithography, a fab. So the ambient is in a yellow color, yellow light, and that's a reason for that. Uh, it is a photosensitive process, so it's sensitive to light, so um, it has to be conducted within a yellow light condition. So this is the examples of the equipment that you can see on the left and on the right. Um, this is called track process or track equipment. So a little bit later, we're going to learn on how do we do CED process, code expose and develop, which is the heart of a lithography process. And to be able to do this CED process, you need to go through a track, right, as shown by this image. To be able to do a lithography process, few things are needed. The first one is a reticle. So a reticle is actually a mask containing patterns that you want to print on your silicon. So the reticle is defined before the fabrication process is done. So it needs to be done. It can be done in-house. It can also be done uh, externally. So that means outside of the company. So it has to be done beforehand. So once it's ready, so we can then proceed with the printing process by lithography. So on the right hand side, this is the example of features that you want to print on your silicon. So you can either print lines, as you can see on the right there, as you can see on the right here. You can print lines, so a straight line here of certain width and certain length and certain spacing between the lines. And you can also print holes, so as shown on the left hand side here. So you can also print holes of certain diameter, and these are printed. No, these are already defined on the reticle before you do the lithography process, right? So we're gonna see later on at what step do you print lines and what other steps do you print holes? So I said before that you're gonna need to measure the line width, or it's called critical dimension in lithography. So, or we typically call it as a CD, or critical dimension. So it usually reflects the width of the line here. So yep, so the width of the feature, that is, if you have that feature, so the width of the feature is called line width or CD. So if you talk about a hole on the left hand side, so it usually refers to the diameter of the hole. So it's also called CD, or critical dimension. Okay, to be able to do the printing process, you need to use light of certain wavelength. Okay, so if you look at this electromagnetic spectrum that you've learned before, ranging from gamma on the left hand side, which exhibits the highest frequency, to the radio wave on the right hand side, which has the lowest frequency, and the wavelength of this spectrum is opposite. So if you talk about gamma has the lowest wavelength, and radio wave has the highest wavelength, has longest wavelength. Okay, so to be able to do the lithography process, we usually use illumination source in the visible and in the UV region, Okay, so uh, the typical sources range from, the older version of the lithography source use 400 plus nanometer. So that you can see on the right here, G line. This one is called G line. So which uses 436 nanometer as the illumination wavelength. So as the process evolved over the years, so Fab moved to H line of 405 nanometer, and then I line 365 nanometer. So when I first joined Silterra back in 2003, so Silterra had I line process and also DUV process. So so I line is 365, and then slightly more advanced version of that is called DUV, or deep UV process, which has a 248 wavelength, 248 nanometer wavelength. Then this DUV evolved to another version of DUV, 193. And then we also have ARF 193, which uses argon fluoride as the light source at 193. And we also have 157. So these illumination sources or wavelengths can also be summarized as what you can see in this table. Okay, so 436 belongs to G line, which uses mercury arc lamp as the illumination source. 405 H line also uses mercury arc lamp. 365 I line also uses mercury arc lamp. So when we move to 248 or DUV, so the system uses KRF excimer laser. So it's krypton fluoride excimer laser, or KRF. So when you go to 193, it uses ARF excimer laser as well. So you can see as you move below I line, is all based on excimer laser illumination system. So 193 belongs to ARF excimer laser, and then if you go for 157, it uses fluorine-based excimer laser. So if you talk about the latest version of the lithography system, it is based on extreme UV. So EUV there, down there, is extreme UV lithography. So the illumination wavelength is only 13.5 nanometer. So if you look at the illumination wavelength, roughly you can say that if you want to print a circuit pattern of maybe CD of around 200, so you need eye line, because normally, well, roughly you can calculate if the wavelength is lambda, then typically the smallest feature that you can print on the wafer with good resolution is somewhere about wavelength divided by 2. So if you talk about eye line, so 365 divided by 2 is somewhere 180 nano. So you can print somewhere around 180 or 200 with good resolution. So if you want to if you want to go below 100, if you want to go below 200, for example, 200 nanometer feature CD on the silicon, so you need to move your illumination system from eye line to deep UV. And with deep UV, if you're talking about 248 nanometer as your illumination wavelength, so you can print down with good resolution on the silicon with feature CD of somewhere 120 nanometer or so. So if you want to go below and below and below, you then have to move to a more advanced lithography system. So if you talk about the latest CD on the chip, the latest technology node that we have in the market. So now we have a technology based on CD of 705 nanometer, 705 nanometer, produced by TSMC, Taiwan Semiconductor Manufacturing Corporation, which utilizes EUV lithography system with illumination wavelength of about 13.5 nano. Okay. Okay, to be able to do lithography process, so for your information, lithography consists of 3 main steps. I'm going to show you later on. So these 3 steps are classified as coating process, exposure process, and also development process, or we call it CED, coding, exposure, and development. So what you have to do, essentially in the first step, you have to you have to coat your silicon or silicon with oxide, for example, with photoresist, which is light sensitive polymer on the whole surface of your silicon or silicon with oxide. And then the C is done, the C process is done, or coating process is done. So then we move on to exposure, where we use exposure system based on the wavelength that we've discussed on the previous page to expose certain areas of your photoresist on the wafer and to block some other areas on the wafer from the exposure, so that you can eventually have patterns after the development process. So the moment you have done selective exposure on the photoresist, all right, you will actually trigger some reaction on the area that you exposed, and there's nothing happening on other areas that you did not expose. Then this can be seen as illustrated in the left figure here. So just imagine that if you have a DUV system, so your UV light here has wavelength, illumination wavelength of 248 nano, and then you have your reticle here that we've seen on our earlier pages, the mask that you have to use in order to define your patterns. So this reticle actually allows a transmission of the UV light through some regions of its surface, and it will also block transmission of the light from on some other areas. So some areas will be allowed for the light to pass through, and then some other areas will be blocked. So the UV light will actually be interacting with the photoresist on the silicon in the areas where the transmission is allowed. So if you can see here on the frame area, the transmission of the light is allowed, and then in the central region of the reticle here, the transmission of the light through the reticle is not allowed. So the interaction of the light and photoresist only takes place on the edge of the sample that we're talking about here. Okay, so what happens next is the wafer is going to go through development process uh, where it actually depends on the type of photoresist that you use for the process. So if you use a negative photoresist, so you have to be clear about this. If you use negative photoresist, so the area that you exposed, so in this case, the outer edge here will be hardened. So the photoresist will be hardened, and the area that you don't expose in the central region here, nothing has happened, right? So you're gonna be left with hardened photoresist on the edge and a softer version of photoresist in the central region. So if you move your sample into development process where it will remove some portion of the photoresist. So in this case, the hardened photoresist on the edge will not be removed, but the central region resist, which did not have anything happen due to the blockage of the UV light by the reticle, will be removed by the development solution. Okay, so typically for the development solution, we use TMAH, or tetramethyl ammonium hydroxide, TMAH. Then after the development process, we're going to be left with a pattern on the outer edge of the sample made of photoresist on blanket oxide that we have grown before in our thermal oxidation process on silicon substrate. So you're going to be left with U-shaped photoresist hardened on blanket oxide and on silicon substrate. This is what happens when you use negative photoresist. So let me just recap. For negative photoresist, exposed areas will be hardened, unexposed area will not be hardened. Okay, so the hardened area will not be removed during development process. The central region in this case will be removed by the development process. On the other hand, if you talk about positive resist, so it was negative resistance now, so it's now positive resist. If you use this kind of pattern, this kind of reticle, which is of opposite characteristic. If you look at the previous slide, the central region blocks the light, and the outer region allows the light to pass through. On the other hand, if you use positive photoresist, if you use this sort of reticle, well, you can also use the previous reticle as on the previous page, but you're going to end up with opposite structure. Okay, so let me explain in a few seconds. So in this case, you use this sort of reticle where you allow the UV light to pass through central area, and you block the light on the outer region. So being a positive photoresist, what's going to happen is, in a positive photoresist, the exposed areas will be removed. The unexposed areas will not be removed. So if you look at this particular configuration, since the central area is exposed to the UV light, the central area here will be removed and the outer area will not be removed. Okay, so the central area will be removed, the outer region will not be removed. So to be able to run your lithography process, it depends on either you are using your positive resist or negative resist, and the reticle can be set up like the previous page where you block the light in the central region, or on the other hand, you can also allow the light to pass through the central region. What you're going to have is basically opposite structures. So just imagine if you use positive resist as on this slide, but you use the reticle here, the reticle on the previous slide on this slide. So what you're going to have is basically an opposite structure on the sample. So you're going to be left with a feature on the central region, and you're going to have your resist remove on the outer region. So maksudnya you punya central region will have a step height, you akan ada structure yang lebih tinggi di tengah, dan dekat area tepi itu semua akan remove. On the other hand, kalau you pakai reticle yang macam ni, then you're going to have a step height on the edge, but the central region will be removed. Okay, so that's the effect of a negative and positive photoresist. So you need to be clear of that. So let's look at the mask and the photoresist. If you want to have desired photoresist structure to be printed on wafer like this, the one on the top, if you want to have that plus sign feature on your substrate, for example, so what you have to use is if you go for the bottom left reticle or the mask, in order to have that structure, that feature on the resist, you have to use this mask in combination with negative photoresist in order to have this feature in the center. So if you can see on this mask, the window is in the central region and the chrome area is in the outer region. So what's going to happen during the exposure is the window is going to allow the UV light to pass through. So you're going to have your light passing through the central region and cause hardening of the negative resist in the central region, and therefore the central region will not be removed during the development process. Then you're going to end up with this feature on your substrate if you use this mask with combination of negative resist. On the other hand, if you want to print this structure or this feature on your substrate using positive photoresist, what you have to do is you have to reverse the properties of your mask. So in this case, quartz is used on the outer region, which allows the light, and the island is in the central region. So the island will block the light from passing through, and the quartz will actually allow the light to pass through. So on positive photoresist, just like what we discussed just now, the illumination will cause the exposure to the resist to cause the areas to be soluble. So these outer regions will be soluble after the development process, and this island area which blocks the illumination from reaching the resist will not have anything happening. So we're going to end up with this feature on the substrate eventually. So to be able to have this feature on the substrate, you need to use this mask in combination with positive photoresist in order to have the desired structure. So you can also look at these masks from 2D just like this. It can also be labeled as categorized as a clear field mask or dark field mask. Clear field mask is where you the white regions here on the outer region is a transparent area which allows the light to go through. So that means if you have your mask like that, this outer region will allow the light to pass through for the reaction with the positive resist. So if you have these areas exposed, so this one exposed, this one exposed, but on the other hand, if you look at these lines and these rectangles, three rectangles in the central region, and these lines, these features will not be removed after the development process because during the exposure to the light is blocked from reaching these areas. So these areas will not be soluble, and the white areas here will be soluble. Then you're gonna be left with these features on your substrate. On the other hand, if you want to print holes, so on the left hand side is now we printed lines. So on the other hand, if you want to print holes, so you have to use a dark field mask. So dark field mask usually composed of this dark field. So majority of the mask is made of dark field. So these dark areas or the gray areas are the regions which block the UV light, and these white square areas are the areas which allow the light to pass through. So the reaction on the positive resist will actually take place, will only take place on through these areas, on these areas if you like. Okay, so you're going to have these areas, these square dots are removed after the development process, and these other areas will not be removed after the development process. Then you're going to print your holes, and your line accordingly, right? So that's the role of clear field mask and dark field mask in lithography process. So as I said just now, the lithography process uh, is usually called a CED process. So where the C belongs to coating process, E belongs to exposure process, and D belongs to development process. So the key main categories are categorized as CED, or coating, exposure, and development. Even though the key steps are actually three, each C, E, and D, they actually have a couple of steps, a couple of minor steps in between. So essentially, if you talk about a litho process, they can be divided into 8 main steps. So we're going to go through one by one later on. But for this particular summary, so let's just look at these 8 main steps. So after your oxidation process, so assuming that you've got your oxide on your silicon, so assuming your oxide is about 10 nano or so thickness on your silicon. So to be able to start your lithography process, so firstly, the robot arms will pick up your wafers and then put into lithography process. So the first step the wafer is going to experience is called vapor priming. So the role of this process is to improve addition of the photoresist, which will be spin coated later on at the next few steps on the resist. So HMDS is actually like a glue layer, if you like. It's just like a glue layer in order to bind photoresist on your oxide or on your silicon more properly, right? So in order to do this priming process, so we use HMDS as the precursor material. So this HMDS, the full name of HMDS is hexamethyldesilazane. So you can Google it up. So hexamethyldesilazane. So the HMDS is vaporized in the chamber at certain temperature for a certain time. Then it will actually coat the surface of the silicon or of the oxide before the resist spinning process. So now the surface of the oxide or the silicon is already glued well before we spin our photoresist. So the next step is the spinning of photoresist. So photoresist is a photoactive compound, so it will react with light of certain wavelength for certain time at certain temperature. So it has to be activated as well. So what we do on the on the wafer is we dispense somewhere around 1 ml of photoresist on the wafer. So typically, if you talk about 8-inch process, we normally use 1 ml of photoresist for every dispense. So that means to fabricate one layer using photoresist, we normally use 1 ml. We dispense and then we spin at a couple of thousands RPM for a couple of seconds. There are a few steps for that. You have to look into the recipe of the photoresist coating process, and then after the process, the wafer is going to be coated throughout the surface. Then the wafer is going to be sent to the next to the next step, which is called soft bake. So what's going to happen is we're going to bake the wafer at about 90 degrees C or 100 degrees C for a couple of seconds in order to remove the residue of a solution during the lithography, during the spinning process. Right? So you want to remove the residue or the solvent remaining in the resist so that the hardening of the resist will take place successfully during the exposure process. So after the soft bake process, now we're gonna go to the E step or the exposure step. So we're gonna use a scanner. We're gonna use a scanner in these particular steps. So we're gonna use our wavelength of choice, for example, 248 nanometer for DUV process in order to expose. Then it's gonna go through post-exposure bake process, which is a PEB, where you bake the structure to make sure that they are strong. and then the features exposed by the UV and reticles now in the scanner process is now developed using TIMA, or tetramethyl ammonium hydroxide, which is an alkaline solution. Now in this process, we're going to remove the areas which are soluble after the exposure process, and we're going to maintain the areas which are not soluble after the exposure process. And then the wafer is going to go through hard bake process in order to remove the residue from the development process. And then we're gonna finish the lithography process, which by a process which we call visual inspection or develop inspect, where you check and you make sure that the features that you want to print are actually printed in the right areas, and you don't have residue of the resin and so on and so forth. Then the lithography process is done. Okay. I'm just going to stop here for this particular slot. So I'm going to see you again in the next class. So bye bye. Salam alaikum.